Alright, let's do a second video on circuit theory questions. We'll do a slightly more tricky example now, and we'll do a similar thing to the last one where we had an imaginary circuit that we just made up. We just found out everything that we could about it. So let's make it a little bit more complicated than in the last one. Okay, as I did in the other one, I'm just writing the resistors like that, because drawing them like that because it's just quicker than drawing boxes. Okay, and let's say that it goes like that. Alright, so in theory this should be like, I don't know, could look symmetrical. Doesn't really matter where you put the batteries, it could be here in the middle. Anyway, these are just cables. So what's happening here? Let's give this, actually let's add a little other resistor up here, why not? Where's the pen? Like that. And let's say that this has 4 ohms of resistance, and this could have 6 ohms of resistance, and let's say that this is 8. And this could be, let's add another one in there also. So we have one resistor in there and another one here. 2 resistors. So let's say that this has 2 ohms and that has 4. And this has 10 ohms of resistance. Alright, so let's say that the EMF of the circuit was a total of something nice and easy to divide into other stuff. Let's say 10 volts of EMF. Okay, and so we're going to draw resistances in that color and voltages in yellow, and currents, we'll draw them in green, why not? And current goes from positive to negative. Positive is the long side of the battery. Electrons go in the opposite direction, as you should know, but the convention says current goes in this direction. Now what's happening with the way the current's splitting up and the voltage through each resistor? So let's figure that out, okay? So we'll do similar to the last question, in which we're finding out everything about the circuit. So we want to find out all the currents and all the voltages. So let's name the resistors first. Let's call this resistor number 1. We'll call this one number 2. We'll call this one number 3. This is resistor 4, that's resistor 5, and that's resistor number 6. Okay, and we need to, I want to find out the voltage, the potential difference across all the resistors. Okay, so I want to find V1, V2, V3, V4, V5, and V6. And current, I want to find out this current there, and I also want to find out the 3 individual currents through these 3, okay? And through here, from Kirchhoff's first law, this current will be the same as the total current going in the circuit, because no charge is lost. So we know that this I and that I are going to be the same, but we're interested in the I through branch 1, through branch 2, and through branch 3. So we're going to call this one, we're going to find I, just the general I we need to find, and then we want to find I1, I2, and I3. Alright, so there's a lot of stuff here to find, and let's see if we can do it all within the space of the video. So what's happening with this? Well, let's use the idea of the equivalent circuit just for simplification, and so that you get practice also. Let's draw an equivalent circuit where, instead of having all these crazy resistors in parallel, we imagine that we've sorted out what the total resistance for the 3 branches is, and we drew another circuit. Simplified version, it would look like this. This resistor would correspond to that one. All of those would correspond to one single resistance that we've just calculated, and we still have that one at the top, and it goes back. So this would correspond to that, this, all of that to this one, and this one to that one. That's an equivalent circuit for that one. And in order to make it work, we'd have to use the same EMF here, obviously 10 volts. This would have to have the same resistance, 4 ohms. This one would have 6 ohms, and this one we don't know yet, but we can find out using our formulas. So as a first task, let's do this. Why is this useful? Well, to find the current going around the circuit, you need to know the total resistance in the circuit, and to do that, it's not so easy to look at this and just know what the resistance of all of that is. So we first find all of that and we summarize into here, and then we can even draw a third equivalent circuit, which is even simpler. So this can be simplified even more, even though it's not necessary. We can still do it where we just have one resistor and back to the battery, and this resistor would have to be a sum of this plus that plus this. So it would be 4 plus 6 plus the R that we're going to find out for the combined resistances here. We'll just call that R. And the current flowing through this equivalent circuit would be exactly the same as the one flowing through this equivalent circuit and through that one over there also. So it's useful to know that, because that's one of the things we want to find out here. I want to find out everything about the circuit. So what's happening? Let's find out that current then, and to do that we need to find out the resistance of all of that. So let's find out those resistances first. What's my formula? Well, 1 over the total resistance that I want is equal to 1 over R1 plus 1 over R2 plus 1 over R3. R1, we said that this was the first branch, so R1 is just 8. R2 is 4 plus 2, because the resistances in series just add up, and the last one is 1 over 10. That's equal to 1 divided by the one that I want. So 8, 6 and 10. Let's see, what's a common factor between all of those? Well, 20 no, 10 no, 20 no, 30 no, 40 no, 60 no, 80 over 6. Well, let's just multiply them all. 8 times 10 is 80, and 8 times 6 is 48, so that's going to be 480. I wish I had a calculator, because I have a feeling that this is going to be more long than it could have been. So what did I multiply the 8 by to get to 480? Well, times 60. So that's 60. What did I multiply the 1 by to get the 6 by to get 480? Well, by 80. So that's going to be plus 80. And what did I multiply the 10 by? By 48. So 48. 80 plus 60 is 140. 188 over 480. Now let's start simplifying this. What do we get if we divide that by 2? Well, 180 would be 90, so that's 94. 480 would be 240. Let's do it again. 490 would be 45, so that's going to be 47 over 120. And I'm not sure if that can be reduced anymore. Wish I would have chosen more simple answers, but I'm just going to put this in my phone calculator, which is not as groovy as normal ones, but it should still give me the right answer. 47 divided by 120. 0.39. And now I do, okay, so 0.39167, blah blah blah. So I'm going to use accurate enough to get some answers. So 1 divided by 0.39167, 2.55. I've done the reciprocal now, so that was 1 over R, and now R is 1 divided by that, and I get 2.55 ohms. Okay, so let's take it to be exactly 2.55. So what does that mean? That means that this R is 2.55. So if this R here is 2.55 ohms, then the resistance of all of that together is 4 plus 6, which is 10, plus 2.55. So the resistance of everything together, this guy there, is the same as 12.55 ohms. So now I can use this and the fact that I know that this is 10 volts to find the current. V is equal to IR, so I is equal to V over R, which is 10 volts over 12.55. Let me do that in the 10 divided by 12.55, that's 0.796. So actually I'm just going to take that to be 0.8. No, that is not the unit of current, it is amps. 0.8 amps is going through the whole circuit, so that's good. Very useful to know, because now we have this guy, 0.8 amps for that guy. Now what can we do with that? Well, it's gonna split when it gets to here into 3. So how do we know how much goes to each one? Well, we need to know the voltage potential difference between this point and that point. And how do we know that? We can't say that it's 10 volts like in the last time, because now there's another 2 drops in potential in the circuit, so we can't assume that. So it's this drop plus all of that drop plus this drop will be equal to 10 volts. How much is that going to be? Well, now that we know that the resistance of this whole thing is just same thing as 12.55 ohms, then we can use this circuit here to know what the potential difference through each thing is. So that's why the equivalent circuits are useful. Instead of looking at this all the time, you can now go to the appropriate one. So this one we used it to find the total current in the circuit. That was useful, and that's being used now. Don't really need it anymore. Now this one is useful for the potential difference through each one. So how do we do that? Well, a current of, what's the current? 0.8 amps is going through the whole thing. So what's the potential difference across this resistor here? Well, 0.8 amps and 6 ohms means that the V of this resistor, which I've called resistor 1, so that resistor 1, we're looking for V1 now. V across there is V1 is equal to current of 0.8 times the resistance, which is 6 ohms. 6 ohms. So let's find that out first. So what do we have there? Well, that's just going to be 4.8. 6 times 8 is 48, so that's going to be 4.8 volts going through V1. So now we found this guy. Got that guy, and we got this guy. Now, what about V2, 3, and 4? Well, let's do V6 first, because this one's easy. It's 4 ohms and also 0.8. So V through resistor 6, V6, is going to be equal to 4 ohms times 0.8 amps, which is going through this one also. It's the same current. So 4 times 8 is 32, I believe. So that's going to be 3.2 volts. So we got V, which one is that? V6. Okay, well now we're missing V through all of these. So basically what I would do here, that is going to be the quickest way, is that if I know the voltage through this guy is 4.8 potential drop, and the potential drop through this one is 3.2, then I know by default, by Kirchhoff's second law, that 10 volts is going to be equal to the sum through of the potential difference between this one plus that one. So I can now just subtract. I can say, well, potential difference between here and there is going to be 10 minus 3.2 minus 4.8. So that equals, well, 3 plus 4 is 7, 0.2 plus 0.8 is 8, so 10 minus that is going to be 2. So 2 volts is the drop through this whole thing. Why is that useful? Because there's a drop of 2 volts from here to there, and from here to there, and from here to there. It's the same drop for all of them. So I can now know that this is 2 volts. I can now solve for all the resistors. Again, I'm running out of time. It's nearly 15 minutes, so in the next video I'll finish getting all the currents and all the voltages through all of these. Hopefully it's all making sense so far. I'll see you in the next